Welcome to this reinforcement learning, bandwidth, and online decision-making session. So today we will have 8 talks. We will start with an oral talk, followed by 7 spotlights. So the first talk is for the paper Getting Incentives in Recommender Systems, a cooperative game theoretic approach for stable and fair collaboration in multi-agent bandwidth. The speaker is Ramakrishnan Krishnamurthy. So please, the floor is yours.
Good morning, everyone. Thank you for being here. I am Rama, a PhD student at New York University. And today I'll talk about content creator incentives in online recommender systems. So I'll present our work on attaining fair and stable outcomes in recommender systems. So consider a recommender system workflow. Where you have a platform, say YouTube or TikTok, and there is a set of content creators, the YouTube channels, that create a pool of content, the videos that they upload, or the shorts or reels that they upload. And then the platform chooses from this content to recommend to a stream of users. The videos show up as thumbnails in your homepage, or it shows up as videos keep appearing as you scroll down in your app. And then the platform observes the user feedback. That is, if the user clicked on that video, did he like it, did he move away from it, how long did you watch that video, and so on. And with this feedback, the platform then learns something about the user interests and also about the content quality and the genre of the content. In addition to this, the platform also then pays the creators, compensates or gives pay or incentivizes the creators proportionate to how well their content engaged with the users. Now, to see the fairness concern here, let's take a small example. Let Alice and Bob be two content creators, and Alice creates a content about apples and Bob about bananas. And there are some other content in the platform as well. Now a new user arrives in the platform. Say the platform recommends apples to the user initially. Simplistically speaking, there are two outcomes. The user might like this recommendation or dislike or not like this recommendation. Let's take the first case. Let's say the user likes this content about apples. Alice is positively compensated because Alice's apples did well with the user. Then the platform generalizes, learns that the user is perhaps interested in fruit-related content, and in the next interaction recommends Bob's banana to the user. And as the user is likely, he will also enjoy the content about bananas. He likes that as well, and Bob is also positively compensated. So here, Alice is happy, Bob is happy, the user is happy, and the platform is happy. But despite identical payouts, note that Alice was made to shoulder or take a risk. That is, Alice's apples were recommended when the platform did not know anything about the user interests, whereas Bob's banana was recommended when the platform had some idea about the user's interest in fruit-related content. So there is a dependency. In fact, this dependency is more pronounced in the other case, where the user dislikes the content about apples. Then Alice is negatively compensated, or its payout is negatively affected because Alice did not do well. And the platform now generalizes that the user does not like fruit-related content. And in the next user interaction, it does not recommend bananas, it recommends something else. Now, Bob is happy that he avoided a potentially bad exposure. That is, an exposure to a user who might not have liked this content about the bananas. So all of this is to say that Bob's outcome depends on Alice's presence in the recommender system. So creators' outcome depends on the presence of other creators as well. Now, by how much? What is the marginal value that each creator brings to some other set of creators? To rigorously study this phenomenon, we model this as a transferable utility game, or a cooperative game, or a correlation game, to understand what the values of different subsets of creators are. So it is modeled by a tuple of the set of players, which here is the set of content creators, and a characteristic function that assigns a real number value to every single subset of creators. In our scenario, we say that for every subset of content creators, we assign the value to be the following. We ask a what-if scenario. What if only the content creators in set C and their content was available in the platform with the recommended? Then what is the utility or what is the user satisfaction that the platform could have generated with just this set C of creators? Now we could decompose this user satisfaction among the different content creators by charging the content which generated this particular user satisfaction to the creator of that content. Now let us set aside this value function for a moment. So modeling this entire scenario as a transferability game lets us borrow a lot of nice tools and concepts from game theory, such as the core, which describes the stability of a cooperation game, the Shapley value, which gives us a fair way of dividing the overall utility among the individual players, and the convexity of the game, which has some very nice properties as we shall see. Just to recall, Shapley value is defined as for a particular agent A, it is for a particular player A, it is defined as the marginal contribution that the player brings to any particular subset C. So the value of C with A in it minus the value of C without A in it. And this is weighted over all possible subsets, an exponential number of them. And this Shapley value is the unique solution to a number of nice fairness axioms like the null player axiom, linearity, efficiency, symmetry, and so on. Now these topics are very well studied in the sense that it's been widely used in a lot of different applications, such as explainable AI. How extensively, how much does an input feature really impact the output label? How should the burden of taxation be shared among the different benefactors? Portfolio pricing, how should the risk of an individual asset be divided? And applications in cybersecurity, distributed systems, and so on. So very well used, very well studied. So now let's come back to our recommended system scenario. So to model this user satisfaction, what we do is we use a multi-agent contextual linear banded setup in the regret minimization framework, where we model the content creators as the set of agents, and the time horizon models the sequence of user interactions, and the learner is the platform, the recommended platform. At every time step, the learner plays an action or recommends a content from the action set, which is the pool of all content available, and it observes a noisy reward, which models the user feedback or the user satisfaction, and then it learns the unknown parameter theta star that determines all this from the data that has been generated. And this keeps on happening for t rounds, and the objective of the learner is to minimize the regret expression, which corresponds to the maximum attainable user satisfaction minus the expected actual user satisfaction. So this regret models the negative user satisfaction from A's content, and we use this regret term, and in fact the negative of this regret term, to model the value of the correlation summed over all the different constituent agents. So with this formulation, we then ask for what types of banded problem instances and what families of algorithms does the induced resultant cooperative game described as tuple have desirable nice properties. So first, we looked at homogeneous agents, where it's an idealized setting where all content creators have equal capabilities and they have an identical user base access. So in the banded scenario, it means that the action sets of all the agents are identical. The first result that we have is we design a multi-agent meta-algorithm that when run with a single-agent black box algorithm that obeys some property, the resultant cooperative game is convex. Now we'll get to this convexity in a bit. So the property that we want from this black box algorithm is the following. We want the regret as a function of time to be strictly concave and also not flatten or converge faster than the logarithmic curve. In fact, there are known empirical evidence and theoretical evidence that suggests that a lot of common popular algorithms like the UCD, Thompson sampling, actually have this property. And in fact, there are no lower bounds, information theoretic lower bounds that say that no algorithm can actually flatten or converge faster than the logarithmic curve. Now back to the result of convexity. Now what implication does this convexity have? So let's recall that the feasible set of payouts contains all possible ways of exhaustively or fully dividing up the utility of all the agents among the constituent agents. And the core is a subset within this feasible payouts where every particular subset C of players are being paid at least as much as they can generate by themselves. So if the payout does not belong to this core, then it means that some set C of agents are underpaid and they will want to leave the platform. They'll probably go to a competitor or let's say form their own platform, create their own recompense system. So in general, the core can be empty, but because the game is convex, we know that the core is not empty. And not only that, the Shapley value actually belongs to the core for a convex game. Now this Shapley value as a payout has a lot of very nice properties. All the Shapley axioms get satisfied as a result, and it also belongs to the core due to this convexity. So nice things happen. So what was really the challenge here? So to show convexity, we needed to show the supermodularity of the value function. And to show supermodularity of the value function with the regret definition that we have, we needed to show this inequality, where we need to upper bound the LHS, the regret terms in the LHS, and lower bound the regret terms in the RHS to show this bound. So we need really tight regret upper and lower bounds for this multi-agent setting. And the existing lower bounds and upper bounds, even if they are differing by a constant multiplicative factor, are just not good enough. So that's why we needed a multi-agent meta algorithm that achieves convexity and gets us all these nice fairness and stability properties for the homogeneous setting. Yeah. So what was there was just not good enough. Now, moving on to the more general heterogeneous agents case, content creators have arbitrarily different capacities, like different users in different niches and different subscribers, and they think they are arbitrarily different action sets. We need two properties from the algorithm data. So one is the anonymized data consumption, where the data from each agent can be consumed by that agent, and the data from all the other agents have to be consumed via an anonymized tool that actually strips off the identity of the agent and the time at which the data was generated. Second is the more the merrier property, where we say that for two correlations S small and B big, the regret of any agent as a part of the bigger correlation is at most the regret as a part of the smaller correlation. That is, if more agents join the collaboration, the regret of an agent does not go up. So if the algorithm has this more than merrier property, then we have that the game is stable, that is the core is non-empty. But we still do not know if the Shapley value belongs to this core. So what would be a payout that belongs to this core and is also almost as Shapley fair as possible? So consider this particular payout vector, which is just the negative regret of an agent in the full set of agents collaboration for that algorithm and for that instance. So that is saying that in the recommended system scenario, the payout is proportional to the user satisfaction on feedback that is generated purely out of his own content. Now this is a very natural payout where the agent just keeps his own correlation prepared. So when the learning algorithm follows both these properties, the anonymous data consumption and the more than merrier property, then this payout has desirable stability and fairness properties. So this payout obeys 3 out of the 4 Shapley axioms, all 3 except the linearity axiom, and it belongs to the core as well. So it is practical as long as this payout is given, no creator will want to leave the platform. And it is also tractable. Unlike the Shapley value, which requires computation of an exponential number of quantities and a lot of counterfactual quantities about what if the regret, what if scenario where the regret is from other subsets of correlations. This is pretty natural and pretty achievable. So we get an outcome that is stable and almost Shapley fair. So in conclusion, we model our recommender system as a multi-agent bandit scenario in a transferability setting, and we get some nice fairness and stability results. So we consider, and we consider a very natural payout and ask how should the algorithm behave. And in the future, what we would want to do is in effect some class of algorithms, and then ask the other question, how should the payout be tailored? And there are some ways in which we think it can be extended. So I'll leave you with these questions and in return take some of your questions. Thank you.
So thank you, Rama.